Chapter 7 delves further into quadratics. In the last couple of chapters, we looked at how to solve quadratics by factoring. Now we're going to look at how we can solve all quadratics regardless of the nature of their roots and regardless of whether or not they factor appropriately. The first method we're going to use is called completing the square. So this is the quadratic that we're going to consider. Please keep in mind, this quadratic is set equal to 0, and it is in standard form. That is ax squared plus bx plus c form. So your first step is to isolate the c term on the right. The c term would be this one. That means that we will add 3 to both sides. The next step says that if the a term is not 1, divide both sides by that. So here a is 2. So we are going to have to divide this whole thing by 2. This cancels here and gives us a 4 here. So that becomes n squared minus 4n is equal to 3/2. The next step, we have to take this b term here that we've just created, and we need half of it. And then we have to square that number. So take 1/2 of the new b, square the quotient, then add it to both sides. So half of 4 is 2. 2 squared is 4. So I have n squared minus 4n plus 4 is equal to 3/2 plus 4. What we have done here is we have created a perfect square trinomial. This is the step where we actually complete the square. So now we'll factor the left side because it's a perfect square. That would be n minus 2 squared, and that's equal to 5.5, so that would be 11/2. Finally, we'll take the square root of both sides because that cancels. We get n minus 2 is equal to the square root of 11/2. Remember that it is plus or minus. And then we complete by solving for n, add 2 to both sides. So we get that n is equal to 2 plus or minus the square root of 11/2. A couple of guidelines for my expectations. If you have something like this that you cannot simplify the radical, then you can leave it exactly the way that you see it. However, if we had something along the lines of 2 plus or minus the square root of 25, I would want you to do 2 plus 5 and 2 minus 5. So your answer would actually, in that case, 2 plus 5 is 7, 2 minus 5 is -3. So if this simplifies, I expect you to simplify it completely. If it does not simplify, you may leave it the way that it is. Let's try a couple more. So our first step here is to bring the constant term over to the other side. Then we cut this in half, and then we square it and add that value to both sides. So cutting it in half gives me 3, squaring it gives me 9. By the way, I skipped that second step because here my a term is 1. Now I write this as a squared binomial. Take the square root of both sides. And that's plus or minus 2i. subtract 3 from both sides, and I get x is equal to negative 3 plus or minus 2i. The next equation, not written the way that we're used to having it written, but we can still work through this. What we'll do is we'll bring this term back over to this side. Now we do have to divide by 9. Complete the square. So half of 4 is 2. 2 squared is 4. That would be x minus 2. Negative 35/9 plus 4 will be positive 1/9. Take the square root of both sides. And then add 2. So this is one of those cases that I want you to actually put these together. So 2 plus 1/3, that's 2 1/3, or we can write that as 7/3. 2 minus 1/3, that's 1 2/3, so we could write that as 5/3. And those are your answers. We're looking at a little bit more complicated of a problem, but we can actually still solve this. We're simply going to undo exactly the way that we're used to solving equations. First thing we undo is this big division, so we multiply both sides by 4. Then we subtract 1 from both sides. Then we divide by 3. Now we take the square root. Subtract 5 from both sides, so I'll move up to the side here. Because I've got some numbers, I will actually solve this. Negative 5 plus 3 is negative 2. Negative 5 minus 3 is negative 8. But this is negative x, which means I need to change these both to their opposites, and x is equal to 2 or 8. The last one is definitely a challenge, so I want you to make sure that you follow along with this. Step 1, bring your constant to the other side. Step 2, divide everything by a. Step 3, cut this in half and then square it. Cutting it in half means that we now have b over 2a squared. And that's going to be equal to negative c over a plus b over 2a squared. Now, since we've completed the square, we can rewrite this. And what I'll do here is simplify all of this. what happens on the left, I'll actually show you kind of at the top of your screen. You have negative c over a, and b over 2a quantity squared becomes b squared over 4a squared. And then in order to add these, you have to multiply by 4a over 4a. So you have negative 4ac over 4a squared plus b squared over 4a squared. So that's how we put those together, and we get negative 4ac plus b squared over 4a squared. Then we take the square root of both sides. When we do, we're left with x plus b over 2a is equal to the square root of negative 4ac plus b squared. And when I take the square root of this denominator, I end up with 2a. Then I subtract b over 2a from both sides. Oh, by the way, that's a plus or minus. I'm going to rewrite this so that b squared is out in front. And since I now have the same denominators, we can write this formula that we're so used to seeing. So now you know where this formula comes from. I do not expect you to have to go through that process. You should probably have the formula memorized. In order to use this formula, you will need a quadratic equation in standard form set equal to 0. This is a, this is b, this is c. So to solve for x, this says negative b. This b is negative, so what it really means is the opposite of b, which means you need to make that positive. From here, we see that we definitely get some imaginary roots. We call them complex roots. If you have a complex root, you may leave it exactly like that. I don't feel like I need to show you how to use this formula over and over again. I imagine you've been using it since you were in middle school. But I do want you to understand what it means when we set a quadratic equal to 0. What we're looking for is this location here and here where the graph crosses the x-axis. So these are the values we're looking for. They're actually x values because y is 0. When you end up with complex roots, what that means is that the graph actually never touches the x-axis. So we can come up with complex roots and imaginary numbers, but it's not going to visually show anything on a graph.